കണക്ട് ചെയ്തിട്ടുണ്ട്.
ഓക്കെ ഒന്ന് റൂപൻ ചെക്ക് ചെയ്ത പോലെ ഭൗതിക കേരള അതിന്റെ ക്വാളിറ്റി
മാക്സിമം എത്ര വരെ
എന്നുവെച്ചാൽ അത്
അങ്ങനെ സെറ്റ്
ഇത് ഇന്ന് ഞാൻ 40 ഔട്ട് കിട്ടുന്നുണ്ട്. ലാപ്പിൽ 40 കിട്ടുന്നുണ്ട്. അത് പിന്നെ സ്ട്രീമിംഗ് സോഫ്റ്റ്വെയറിലൊക്കെ നമ്മളിപ്പം പ്രീമിയം എടുക്കുകയാണെങ്കിൽ പ്രീമിയത്തിൽ 40 കിട്ടും. അപ്പം നമ്മൾ പറയുന്നത് ലാപ്ടോപ്പിൽ വാങ്ങിക്കുന്നത്
മൈക്രോഫോൺ ഇതിൻ്റെ ഉപയോഗിക്കുന്നത് അപ്പം അത് നോക്കാറില്ല. ഈ മൈക്രോഫോൺ ഇതിൻ്റെയാണ് ഉപയോഗിക്കുന്നത്. ആ അപ്പം അല്ല പറയുന്നത് സ്പീക്കർ എത്ര സമയം 2 മണിക്കൂർ വേണ്ടി വരും. എക്സ്റ്റൻഷൻ കൂടെ വേണം. സ്റ്റാൻഡ് हमारे 4 एक्सटेंशन
Good evening, ladies and gentlemen. It is my pleasure to welcome you all to this enlightening session on Unlock the Mysteries of the Universe with the James Webb Telescope, which will be led by our very special guest, an expert in the field of astronomy and physics from one of the most reputable research institutes in our country, the Tata Institute of Fundamental Research. I call upon Raghu sir to give an introduction about our guest.
Good evening. It's a great pleasure and a privilege for me to introduce to you all my very good friend Manoj, Dr. Manoj Puravankara, who is now in Tata Institute of Fundamental Research. We know each other since our undergraduate days in Mysore. So Manoj did his masters from the Regional Institute of Education in Mysore, and then did his PhD from the Indian Institute of Astrophysics. And then he had a few stints in postdoctoral research, briefly IUCA, then at the Academia Sinica Institute of Astronomy and Astrophysics in Taipei, and then a fairly long term in University of Rochester, Max Planck Institute for Astronomy and Astrophysics in Melbourne. And finally, he entered the Faculty of Astronomy and Astrophysics in AF. So he is from Calicut, and I have been requesting him to and talk to us. And now the occasion is that he is involved in several projects on the recently launched JWST, uh, James Webb Space Telescope. He'll tell you reasons why he wouldn't prefer to call it that. It's not only on JWST that he works on, he has been involved in various NASA missions like Spitzer Space Telescope, etc. So he basically studies star and planet formation, exoplanets, etc., and works on the edge of our knowledge in a field of intense activity, bordering sometimes speculation. So let's hear Manoj describe that to us today. Welcome Manoj to this NIT channel.
So, so okay. Thanks, Raghu, for those kind words, and good afternoon, everyone. I'm really happy to be here talking to you and sharing with you some of the excitement that has caused because of launching of JWST, of course, and in general, the field of astrophysics. Uh, Raghu and I, as Raghu said, go back a long way back, and he has been sort of a mentor to me as well. I should just mention that here. Anyway, so I'll talk about JWST and what it will do, you know. And what I want to do in this talk is to first tell you what is JWST, then tell you why it's a $10 billion project. So why would we spend $10 billion on a telescope like this? It's a US, Canada, European project. So we are not part of it. I'm part of the international team. That's why I got that. So why would anybody spend $10 billion on a telescope? Going through something new, right? So, and finally, what I'll do is I'll tell you some of the big questions that JWS should be addressing, and I will talk about them in the context of the first light images. Some preliminary results have started coming out of JWST. So I'll talk about some of the big questions that JWST will address in the context of those first light images. I'll show some of the images and explain to you why JWST has caused such excitement all around the world. So what is JWST? It's a 6.5-meter telescope. So in a telescope, what the most important part is the size of the primary mirror, because that determines your sensitivity, how much light you can interact. So JWST is a 6.5-meter telescope, and it's in space, and it works at infrared wavelengths. And all these are important points. I'll look at it individually later, but I just want to give you an overview of this. And JWST has 4 instruments on board. So this is the primary mirror, this is the secondary, and scientific instruments are here. JWST also has a huge sun shield. All this, I'll explain to you why you need a sun shield. Yeah, so just want to say that is a joint mission between NASA, ESA. ESA is European Space Agency, and Canadian Space Agency. Now, JWST was launched on the Christmas Day last year, December 25th, 2021. And it was supposed to go into a point called second Lagrangian point of the Earth-Sun system, or for example, potential zero. So it took a month to reach there. On January 24th this year, JWST reached there at the destined place where it's supposed to be. And then for the last 6 months, until about July or so, not last 6 months, I mean, from January to July or so, it has been, so see, when it was sent, it was not sent like this, as the mirror was folded, everything was in the rocket. If any of you have seen the launch, then it started unflapping the mirror, and the, unfolding the secondary, and also installing the sun shield and all that. So that's first few months. And then it started running calibration tests, etc. And the major science observations in July, and we got our data in July, and we now have a lot of data from JWST we are working on. The primary mirror, as I said, is a 6.5 meter. That's the total diameter, but it's made of 18 segments of 1.3 meter diameter. Why segments? Because it can be folded while put in this space. And this mirror is made of beryllium. Beryllium is the strongest metal for its weight. So it's a light element, but it's strong for its weight. And the substrate is beryllium. On top of it, it's coated with gold, 100 nanometer thick or something, 0.1 micron. That's why it's yellow. Why gold? Because gold is an excellent reflector of infrared wavelengths. Because JWST is primarily going to receive electromagnetic radiation from the astrophysical objects in the infrared wavelengths from 1 microns to 28, 30 microns. And yeah, so the total length, and then you have the sun shield. This sun shield, when unfolded, it's about 20 meter by 15 meter. It's the size of a tennis court. And sun shield is to block the sun, because to detect infrared wavelengths, you have to really cool the telescope and detector. See, I am emitting an infrared wavelengths. See, if I'm at 300 K roughly, right? The room temperature is about 30 Celsius. I'm at 300 Kelvin. I am emitting at 2 microns, 3 microns, or about 10 microns. I'm a strong emitter. So JWST so just to make sure that there are 4 instruments, and 3 of them are both in the near infrared wavelengths. I mean less than 5 microns. One of them goes beyond up to 30 microns. That instrument is called MIRI. That has to work at 7 Kelvin. Because we have to detect radiation at 25 microns. We need to really work at low temperature. So it is done by some cryo cooler and all that. But the other 3 instruments up to 5 micron is done by passive cooling. The sun shield does that thing. It blocks the sunlight. See, if there is no sun shield, it will be at a much higher temperature. See, Earth is at 300 K because it receives sunlight and then it emits and it arrives at equilibrium temperature, right? Yeah. So now, why is such hyper excitement about JWST? Why spend $10 billion? Of course, the science. It address a lot of interesting questions about the beginning of the universe. How first stars and galaxies form. But also, but more importantly, also because it will see every component of JWST requires a scientific breakthrough because we have never made anything like that before. So there are a lot of industrial applications and spin-offs. So it's all R&D. Everything that is what JWST is a product of R&D, research and development. The project started around the late 90s. But but that's not the main thing. That doesn't justify it. But it's because it just captures the popular imagination. See, we all want to know about the human story, right? How did we get? How did we get? How did God begin? So the big question is like, how did the universe begin? How did the first stars and galaxies form? How did the galaxies evolve? How did our galaxy evolve? And in the margins of our galaxy around an ordinary star, how did a planetary system like our solar system form? And how did Earth form? And how did life happen in Earth? On Earth? And the emergence of humans on Earth. And then of course goes into our sociology and other things. But this is the human story, right? A single story. If you were to I think not just the scientists, even the general public is interested in the story. It's a totally fascinating thing. So JW should address some of the big questions, not all the initial questions. When and how did first stars and galaxies form? What is the origin of Earth? How did life form on Earth? Are we alone in this universe? The last question is not very clear whether JW can answer, but it will certainly it's going to try. So that is why all this excitement and that is why this US, Europe, and Canada has spent $10 billion. So this is what who was referring to. See, you would have noticed I was just using the acronym JWST. I was not expanding into James Webb. See, this telescope is named after one of the NASA administrator called James Webb, who was at the helm of the NASA from 60 to 68 or something. The reason because there is a British and with NASA signed by more than 2,000. Now it's 2,000. This number this was in 2021. Of young American astronomers, mostly young, assistant professors, associate professors, and a large fraction of them women, to change the name. The reason because James Webb, during his tenure in NASA and his tenure before in the Department of State, was sort of an instrumental figure in what's known as the lavender scare, prosecuting and purging LGBTQ queer people from central government employment, prosecuting and actually he's also probably responsible for mass dismissal of them. So I have several friends, who have signed this document and solidarity with them. I will hereafter use only the acronym. In fact, what has happened is some of the journals. See, one of our important journals we publish is the monthly notices of the Royal Astronomical Society from UK. They have decided that all of papers in JWST they will only use the acronym in solidarity with the people here. So I just wanted to point this out. So let's JWST is just fine. So why is JWST the most powerful telescope ever built? For these four reasons. There's a large mirror, 6.5 mirror. It operates in infrared. It is in space and it acts like a guide mission. In the next few slides, I'll explain each of these points separately. So large mirror. See, JWST's predecessor was Hubble, right? Hubble's primary mirror was only 2.4 meter. It was a single mirror. JWST's primary mirror, as opposed to, it's about 6.5 meter across, and it's, as I said, it's made of 18 segments. So, larger the primary mirror, larger the primary mirror of the telescope, it does two things. It gives you higher angular resolution. If you remember Rayleigh's criteria, 1.22 lambda by d, larger the aperture, smaller is the spatial scale that you get to solve. Second, it can also collect, it has more collecting area. It goes as R square, right, of the area. So, JWST can collect more light. In fact, the area is about 6 times larger than Hubble's primary mirror. So that is what makes one of the things that makes JWST very powerful. The second is that it operates at infrared wavelengths. You all know what infrared wavelength is, right? So this is the electromagnetic spectrum. That's radio, very long wavelengths, microwave, submillimeter, millimeter, then infrared. Visible is here. So Hubble Space Telescope operated mostly in a little bit of UV and mostly in the visible part. And NASA's Spitzer Telescope worked in the mid to far infrared wavelengths. So JWST will cover this range, about 0.7 micrometers to about 30 micrometers. Or 1 to 30 micrometers.
Sorry, why? So what's
See, first it has a better coverage factor. If you had circular thing, there will be gaps, that's one. But it's also easier to fold. Engineering. So why infrared? See, our universe is expanding. You all know this, right? So it's every galaxy is moving away from each other. It's almost like suppose you take a balloon and put a lot of dots on it and say that they are galaxies. Then you blow up the balloon. What happens? Every point is moving away from each other. And this is what the universe is, from just a simple analogy. So what happens when the universe expands is when the galaxy, light enters from the galaxy, before it reaches it gets redshifted. So it's moving away, right? It's moving away from the simple Doppler shift. It's everything right, but it's moving away. So it gets redshifted. So farther away it is, it gets more redshifted. So JWST is one of the major aim of JWST is to look at the universe when it was very far away. So because and also the speed with which galaxies recede also increases the distance. That's another law. So it's all redshifted. So even the galaxies are emitting in the optical wavelength, visual wavelength, by the time it reaches us, it will be in the infrared. So that is why we want JWST in the so that is why JWST can really see far back whether in very distant universe. And the redshift is defined as the wavelength observed divided by wavelength measured in the lab minus 1. So this is we'll use this later. So this is one reason. JWST operates in infrared, so it can look back or see the galaxies which are far away. embedded in the parietal core. And there's a lot of dust in the molecular cloud. So light will not escape that. The dust will extinguish light, especially in the shorter wavelengths. And so that is what is depicted here. So the star emits light from whatever blue or something, but so it will get scattered. The blue light will get scattered. What reaches you is only red. So it also kind of reddening effect. Because JWST operates in infrared violet, we can penetrate deep into the molecular cloud where the stars are born. So that's another reason why JWST operates at infrared wavelengths. Now, the third reason why JWST is powerful, that makes JWST a powerful instrument is it is in space above Earth's atmosphere. So I just showed you here this cartoon. Sun is here, Mercury, Venus, and Earth is here, right? That's about 150 million kilometers. This L2 point, Lagrangian 2 point of the Sun Earth system is here. So Earth is here. So it's on the other side of Earth. For comparison, Hubble is in a low Earth orbit. It's about 570 kilometers from Earth. Hubble is going like this. But JWST is here, L2 point, about 1.5 million kilometers. So Sun is here, and JWST on the other side. That is why it needs a shield. Sun shield will block it like this. I'll show you. Yeah. So that's the L2 point. Sun, Earth, and JWST actually go around the L2 point. It will not be static there. And it has motors to do that. So sun shield will always block the infrared emission from the sun and the Earth. And it will only look at observe the sky from that side. That's the idea. Alright. So what happens is when you have so this side of the sun shield will be very hot, 85 degrees Celsius. So that's about 350 K or something. But on the other side, it will be about 40, 50 Kelvin. Some of these instruments has to work at 40 Kelvin just by passive cooling. So this side will be very warm, which is facing the sun. This side, the other side. So that is the purpose of the sun shield. And the sun shield is made of a very interesting material called Captain. It is a material developed in the lab, I think, in the 1960s or something. It has amazing thermal properties. So it doesn't. It's very stable between 5K to 650K temperature, and it doesn't burn or melt at high temperatures. So it's made of that. Now the fourth reason why JWST is such a powerful instrument. So this is the concept that you should really understand if you would understand cosmology. Something we astronomers call the look back time. In essence, what it means is when you are looking deep in space, you are looking back in time. And this is because of the finite speed of light. The universe is huge, and light has a finite speed, so it takes time for information to arrive at us. For example, it takes 1.3 seconds for the light to reach from moon to us. And it takes 8 minutes for the sun rays to, or the sunlight from sun to reach us. What it means is, if sun disappears today, this is not about today, this instant, it will take 8 minutes for us to know that. That's what it means. So it takes time. Light has finite speed. It's not instantaneous. Now, the closest star to us is Proxima Centauri. It takes 4 years for light to reach us. So if you are in Proxima Centauri also has a planet. If you go there and look at Earth, you will see what it was 4 years ago. Same with Andromeda, the closest galaxy to us, 2.5 million years. So light takes 2.5 million years to reach us from Andromeda. Again, if you were to go to Andromeda and look at Earth, what will you see? Our ancestors discovering fire. 2.5. So just imagine. So JWST uses this the other way and work as a time machine. And finally, this is the Virgo cluster, the closest cluster of galaxies from us. It's about 65 million years ago. If you were to go and look at Earth, you will see dinosaurs. They went extinct 65 million years ago, right? So this is the principle of look back time. And JWST is a time machine because of that. It can really look at the faint objects which are redshifted. So it is seeing galaxies which are just forming at the beginning of the universe. So when astronomers use a telescope to look further away, especially usually farther even further distance, they're also looking back in time. So, when you look back in time, those galaxies are also moving faster. So their light from them is more and more they're shifted. So you really need to work at infrared wavelengths. So these four things, the large mirror, it's in space, it operates in space, and by the infrared wavelengths, and it acts as a time machine. These are the four major reasons why JWST is such a powerful telescope. Now, uh, four major science themes that JWST will study are the following. Early universe. So this is one of the first light image. JWST look deep into this is a 15 hours exposure. Everything that you see which do not have this 6 spikes, they're all galaxies. Our universe is full of them. There are over several thousand galaxies in this image. It's a small part of the sky which is 1/8 of the size of the moon. Just looking at that, and you're seeing several thousand galaxies. It's just 15 hours exposure. JWST can do much more. So redder galaxies are older and smaller. See? And then, so JWST will certainly study the beginning of how did first stars form in our universe, how did first galaxies form in our universe. But it will also study galaxies, the evolution of galaxies. Once it formed, how is it evolving? See, one interesting thing is that our galaxy, Milky Way, is still forming in some sense. Things are happening in the outer parts of our galaxy. It's accreting smaller galaxies into it and all that. So, yeah,
So this is infrared in the how process it like.
I'll come to that. Yeah, you can't see, right? But you're seeing this galaxy. Good question. I'll come to that. Yeah. Just wait for 2 minutes. So galaxy evolution. That's another thing. Just to quench your curiosity, JWST has infrared detectors, powerful infrared detectors which can detect infrared light. So you get the spatial distribution of intensity, and it can do that at different wavelengths. So what we do is we assign a color to a particular wavelength and combine them. And color is a visual concept. Color is completely a visual wavelength. There is no color in radio. It's basically wavelength. So we give it a visual color. So the shortest wavelength we give it blue, longest wavelength red. So that's what we are able to do. So the red that you're seeing here is the longest wavelength, very 20 micron wavelength. The bluest thing that you're seeing here is at 1 micron. So we are just proceeding. I have more to talk about it later. Get the evolution of galaxy, then stellar life birth and their life cycle. How do stars form? And other worlds, exoplanets, planets orbiting stars other than the sun. I'll probably cover only these two. If time permits, I can talk about the other. Early universe, the cosmic history. So this is how we think our universe formed. In the beginning, there was Big Bang, and then it was so hot that everything was ionized and all that. And at around uh, 300,000 years or so, years after the Big Bang, in this phase, it's all ionized. So radiation and matter was in equilibrium. Nothing can escape. We don't know anything about. We can never know anything about this because no light can escape from here. But at around 300,000 or 400,000 after the Big Bang, electrons combined with protons to form hydrogen atom. Universe became neutral. Then photons started flowing freely out to us, and the photons that travel from here is what we observe now as the cosmic microwave background. The 4K radiation. It's coming from everywhere. Anywhere you look, that's the smallest signal that you can observe. That is coming from here. And once it became neutral, it also we didn't so then the what we see in the cosmic dark ages began. So somewhere during this time, the first stars and galaxies formed, and then universe lighted up again. So, and it is this epoch that we know least about the cosmic. And then this is what JWST is going to happen. Uh, JWST has already observed galaxies in this redshift range, somewhere here. So it will observe many more. So we are beginning to, so JWST is observing galaxies which are only 300, 400 million years after the Big Bang. This is big. So we can directly compare some of our models, already ruling out some of the existing models. Because it can, see, even if you detect one galaxy at the redshift of 16 or somewhere here, that time is what? About, few hundred million years or so. Then some of the models are you can already because we don't expect such huge galaxies there at that early in time. Yeah, so this was the JWST deep field that I talked to you about, thousands of galaxies. And now I come to your question about oh no no I just want to add that this is the deep field I talked to you about. The JWST also can do spectroscopy. So from this field I told you some of the red galaxies are really far away, the universe is very young. Now you can confirm it. So you have JWST has a multi-object spectrograph. So each of these galaxies you can take a spectra. So for example, this galaxy here, you see this pattern. This is hydrogen alpha line, and this is hydrogen bomber alpha line, the first 3 to 2 line, and then this is 4 to 2 line, and this blue is the oxygen line. We know the wavelengths of these lines in the lab, and here it's at a redshift of I think 4 or something, and so by the time you reach here, this is our redshift of 13 already. So you see these lines, the whole pattern. This line is gone out of the frame here. So this is the redshift I'm talking about. Because we know the fingerprints of elements very clearly, we have measured them, we can see this pattern. So we can identify. So you see how the redshift. So this galaxy, which is measured here, which is really old, this one. The old meaning it says really redshift is very high. So this is how JWST measures or confirms how far the galaxy is. So the redshift and distance are the same thing. When they are farther away, they are also moving faster, the redshift is also higher. So JWST has already observed galaxies in this range. So with Hubble telescope, we have observed something, a galaxy 500 million years after the Big Bang. But JWST is already observing it a few hundred million years after the Big Bang. So this is already making a lot of progress and a lot of implications for the models. Now we come to your question, how do we see? So JWST has, if I time permits, I'll talk about this instruments, but this has detectors specifically designed for JWST, which is called the memory cadmium tellurium arrays. These are the most sensitive detectors for infrared wavelengths, and they can detect IR light and provide the intensity distribution as a function of space x, y, and light is also triggered at different filters. You see here. You can read, so that's about 1 micron, 2 micron, 2.7 micron, 3.5 micron, 4.4 micron. So 1 micron is given in blue, 2 micron, 2.7 micron in green, and this 4.4 micron in red. And you combine all of them. So these colors, red, blue, and that is only that's specific to our eye. No, there's no other meaning to this colors. So this has been displayed for viewing. So actually what you're seeing is that the red is at 4.4 micron. The photon filter is 4.4. So, but this is how you prepare it for viewing. And same here, this is also, so we call them false color image. See, color is a property of visual wavelengths. This is red and blue. We are calling it blue. Now, other wavelengths, blue and red only means blue means shorter wavelengths and red means longer. That we use it in that sense. So, for example, we also talk about Doppler shift in radio wavelengths. We call it blue shift when the wavelength decreases and red shift when the wavelength increases. So, this is all because we all start out in visual wavelengths, no? Because until 19th century or so, only detector we had was this light. No, photographic plates emerged only in the second half of 19th century. So we call it a false color image in the sense these are not true colors. We can't see it like that. This is not visual wavelength. This is infrared. But as you can see the filters, this is at the 4.4, same way. Yeah. So now I talk about the contribution of JWST in the field of exoplanets. As I was telling you, exoplanets are planets orbiting, yeah.
In that case, we have to see some of the galaxies are seem to be similar.
Similar, how similar?
Similar means some of them are reflections of this.
So see, there are, so I didn't want to get into that. See, you see this peculiar shapes. So this is a process of gravitational lensing. So there is a very strong gravitational, this is a cluster center here. There are several bunch of galaxies here. We're not resolving it. It's a very high mass galaxy. So that is actually lensing the, bending the light from galaxies behind it and producing lensing effect. You can see this distortion. So these both the arcs that you see here and here are the same galaxy because the light is bent around this massive. So this comes about from GR, general relativity also. When you have a very massive object, there is space-time flow, or light bends around. So that's called gravitational lensing. Yeah, so that's what we mean. So if you take, how do we know this? We can take a spectra of this and spectra of this, and you find them for the same redshift. So they have done that in the other glass section. But not in this figure, but they have done. This deep field was 15 hours JWST, but it can go more. But Hubble also did a deep field, so that was 8 days. Just there, as a fact. So JWST is not 15 hours, we can be good to get exoplanets. So as I was telling you, until 1995, we knew only of one planet system. And in Science, I showed our planets, right? Solar system planets, Mercury, Venus, Earth, Mars, Uranus, Neptune, Saturn, Saturn. Yeah. And in 1992, in fact, in 1992, we had discovered planets around other stars, but around a dead star called a pulsar, a neutron star. That was the first extrasolar planet. These two. It's from a different method. But then it was soon, there was research that it became clear that it's not very common. Planets around pulsars or dead stars are not very common. Then the first star around the sunlight, first planet around a sunlight star was discovered in 1995. A Jupiter-like planet around an orbital distance, but very close to the central star. About 0.1 AU, 0.1 times the Earth's sun distance. This was the situation in 1995. 8 solar system planets. This 2 against for the there's another one right around pulsar, the same pulsar. But we haven't detected anything else, maybe one more. So this was the first planet around the sunlight star, the main sequence star, as we call it. Situation 2022 is this. So we now know this number is even this was as of 2nd August, but this has gone to 5,100 or something. So these are various repairs of discovery. I will not go into that, we don't have time, but once we can talk about it offline. So it looks as if planets are very common. We are nothing special. These are the items that we could detect, but the detection is very difficult. So if you sort of parallel the completeness and map out the selection bias and the observation of other biases, it looks as if every star in the galaxy has a planet or perhaps more than one. Now, what will JWST do with this? So JWST, see whether if the planet is a transiting one, the orbital plane, so this is the star, and the orbital plane of the planet is perpendicular to the rotation axis, and we are here. So this is a star, this is a planet with an atmosphere around it. So when it is just into the starlight can pass through the atmosphere of this planet. And if you take a spectrum, you can actually see what is in the atmosphere, the composition of the atmosphere, right? So generally speaking, it's a very difficult experiment to do. With ground-based telescopes, it's not that easy. But JWST can do that. So this is what happens, the starlight actually dips when the planet crosses it. But at the same time, during this dip, if you also take a spectra, then you can see the JWST already done this. You can actually see water lines, water, there's a water vapor in the atmosphere of planets. And also recently it has detected carbon dioxide. But water and carbon dioxide are not really biosignals. here is looking for what? See, one of the biggest aim for exoplanet research is to look for signs of habitability in Earth-like planets elsewhere. Can there be most life? By habitability, I mean, is it hospitable? Will it be hospitable for life? And how do you know that? How do we learn about it? You, from this atmospheric spectra, you see, look for biosignatures. And what are the biosignatures? We know from Earth, Earth definitely most life. From Earth, one of the biosignatures is oxygen, O2 and O3. And then, see, water and carbon dioxide are not really, they are there in that level, but they can also be produced by biogenic processes which are not biological. See, for example, here I show you, see, this is Earth from the beginning, the archaea, prebiotic to biotic. You see here, the blue is oxygen, okay? The green is oxygen, light green. The dark green is carbon dioxide. You see the first 2.5 billion years of Earth, carbon dioxide dominated. Life was not possible. And water is blue. It is more or less constant. But you see, around between 2.5 and 2 billion years ago, something happened. Carbon dioxide went low and then oxygen started picking up. And now, as you know, oxygen dominates everything else. So what happened here? Life happened. So this is what we believe. And we are looking for signatures. That is why we are looking for signatures for oxygen. Any Earth-like planet which is habitable, which is as old as Earth, then oxygen is the thing. Water and carbon dioxide will not tell you very much. And ozone too. Ozone also is it's fun after sunlight it starts picking up. But in the very early times, so in the late times it's O3 and O2. But in the very early times, the planet is yet methane is the bio signature. It produces methane. It takes a while to produce oxygen. So there are these are some simulated spectra that to see what JWST is. This is not real spectra. For prebiotic Earth, is full of methane and CO2 and water. And modern Earth being any planet, Earth-like planet, 4.5 billion years old, as old as the Earth. You see oxygen becoming prominent. So JWST will be looking for this, and maybe they will observe. There's again some other spectra that. Yeah, so I will stop here and just flash the main science status of science themes of JWST. The first slide and realization, or the formation of first stars and galaxies, evolution of galaxies, what are those stars and planetary systems, and the origins of life. I think I'll stop here and take questions. I have some additional slides. The discussion goes in that direction. I can show.
So, often open for questions.
Yeah.
There is a country for
Uh,
suppose something like an astronaut comes in this case.
so in L2, that frequency is very small. See, big asteroids won't be there. See, it's at L2. But small micro meteoroids can, they can, but some shield is okay. But I think, if I don't know if you read about it, so there's already a micrometeor hit on one of the weather segments, primary weather segment. It's larger than what we were expecting, but still by adjusting the mirrors, you can still get the required specification. See, as I was showing you this primary mirror, each of the segment has segment supports. There are actuators behind it. You can adjust it to get whatever shape, so you can do that. But sun shield is okay. So big asteroids we don't expect that.
You don't require